All right, everybody, let's keep moving along here. Let's see. So the next one you guys asked about is number 31 here in chapter 34. So let me find that one and read it. Let's see. It says here that a 15.0 milliwatt helium neon laser of wavelength 6328 emits a beam of a circular cross section that has a diameter of 2 millimeters. A, find the maximum electric field in the beam. Okay, let me emphasize what we kind of derived right before we ended session 2 today. I'm trying to recall what I did with that paper that I worked it out on. Right here. And without kind of repeating that and just encouraging you to go back to section 2, problem 28 there, I kind of go through an argument here that's the same as your book and it's the same as the lecture that says that momentum is a bit more complicated than just MV. That's how you first learned it. But light does carry momentum. And because of that, when it hits or bounces off, it implies a change in momentum, which is a force. And so change in momentum is a force. And the best way to kind of then think about it in terms of electromagnetics is to look at what I'd call a little more advanced topic than physics 121, or at least mechanics, and that the change in energy with space is the same as the change in momentum with time. And since light carries energy, it also carries momentum, and they are mathematically connected. And so we went through and we came up with this formula that we said the pressure is the intensity divided by C, and the momentum is energy over C. So on this one, when they say find the maximum electric field, I guess we don't quite need that quite yet, and maybe we don't, but the intensity then is also equal to the energy density times the speed of light. And I think that's what we want here for A. Let me just think it through here. Find the maximum electric field. Okay, so the intensity would be the power of it divided by its area. The energy density would be 1/2 epsilon naught E maximum squared, and C would be the speed of light. So if we put in the known values, here they said the power of the laser, so 15 milliwatts, is emitted on a circular beam. So it would be striking and making a circle here. So its area would be the area of a circle, pi r squared. And they say the diameter is 2 millimeters. So that means the radius would be 1 millimeter, which I will write as 0.001 meters and square it. So there's the intensity. As we put in the permittivity of free space, we can then have everything except for the value of the electric field. So that is the question at hand. What is the maximum electric field of this laser? All right, so I'll start over here with my calculations on the left, 15 milliwatts. Divide that by pi, divide that by 0.001 squared, and that would be the intensity of it. Multiplied by 2, divide by the permittivity of free space, also divide by the speed of light, and that would then equal the electric field squared. So taking the square root gives me at about 1,896 either volts per meter or newtons per coulomb, whichever you prefer to write your units. And usually something like this, volts per meter, is probably a better way of you talking about the units. B, what is the total energy contained in a 1 meter length beam? Okay, well, remember what energy density is, mu, which is this 1/2 epsilon naught E maximum squared. This is the total energy. And so total energy per volume. So if I kind of draw a picture of a beam here, it would be this cross-sectional area, which would fit with this, and then the length is 1 meter. So why don't I do the energy density and then multiply by its volume, which would be pi r squared times the length of 1 meter, and then move that to the other side, and that would be the total amount of energy in 1 meter's worth of length. So I already have the electric field from the calculation in A, so let me square it. I'll multiply it by the permittivity of free space and multiply that by 1/2. So here's the energy density, 1.59 times 10 to the negative 5, and that'd be joules in 1 cubic meter. So let me multiply by how many cubic meters I have. So times, and this would be that volume, pi times 0.001 squared times 1. And so we are looking at about 5 times 10 to the negative 11 joules. And so there's the energy in that beam. 1 meter of beam. Now, C, this is where our little derivation, it says, find the momentum carried by this 1 meter length of the beam. Well, so here's where I'm going to go back to the problem we did before the break. And so number 28, where we had this long discussion, and we said, look, force, kind of people have this intuitive feel for, but it really is something a bit more complicated than just a push or a pull. And in chapter 8 in Physics 121 and in chapter 9 of Physics 121, we said the force was related to these. Here we said it was how the energy changed with position. And over here we said how momentum, P being the momentum, that can be misleading because there's a P for pressure, a P for momentum, and a P for power. But this is supposed to be momentum. So how the momentum changes with time. And then if we just kind of drop that, set them equal, do a little calculus, we come up and say the momentum is energy divided by C. So we know that, and this is kind of the best way to describe to somebody that a beam carries with it momentum and a force, because they do buy into the fact that a laser beam carries energy. And so this is saying if there's an energy, there's also a momentum. And they just focus on momentum as mass times velocity, kind of what works for particles, but doesn't work for light. That just could drive somebody crazy. And for many of you, this is the first time you're coming across this notion. And so you're so used to doing momentum in terms of particles. You're so used to saying that the momentum is mv, when in reality, the momentum is a bit more complicated. The momentum is how it is a quantity that changes with time, directly how the energy changes with position. So anything that has energy then has momentum. So our light beam, our laser beams, our radio beams, our sunlight, they all have with them some momentum. And you can see down here that the energy divided by C, so, like a laser beam or even sunlight, you walk outside and the sunlight hits you on the face, at least there's enough energy that you can detect it. You say, oh, the sunlight feels warm, especially on a cool day. Like, oh, yeah, that feels so good. I can feel that energy. But take that amount and divide it by a huge number, the speed of light, and that's how much momentum it has. And that's not much. So it's hitting you in the face, but you don't feel like it's making an impact. All you do is feel like you're absorbing energy. And it almost comes across as if you have energy and no momentum. But I'm trying to say you can't have that. You have more energy, you also have momentum. They go together. And that's what this proof is. So the sunlight that hits you on the face, or in this case, it's a laser beam. If this laser beam were to hit you, 15 milliwatts over that area, you might be able to feel a little bit of warmth. I don't think it'll burn your skin, but you would feel that energy. But you take that and divide it by C. That's such a small amount of momentum. You're not going to feel the beam hitting your hand. Anyways, I probably talked too much about it again, but that's why I went through all of this. And so what that means I can do for this problem, where it says, hey, find the momentum. How much momentum is in this 1 meter of beam? I could just take the energy and divide it by C. And the energy is what we just did up here in part B. So, all right, I got that energy still in my calculator. It wasn't much energy in that 1 meter. Let me just check. Are they still talking about that 1 meter? Find the momentum carried by that 1 meter length of the beam. Yeah. So it's already a small amount of energy. I can't imagine you feeling that. Fortunately, if you were to put your hand and shoot it, within a split second, many meters would hit you. So you would get far more energy than this. This would not be enough to register. So if you only let 1 meter hit you, you wouldn't even say, hey, I felt warm, I felt anything. But remember, in 1 second, it would be 300 million meters of the beam would hit you. And that would be quite a bit. It still wouldn't be that much energy, but it would be enough that you would feel. But now when you divide it by the speed of light, it's just so incredibly small. It looks like we're talking about 1.67 times 10 to the negative 19. And if you remember the units for momentum, they would be kilogram meter per second, which of course you can see here with a joule over a meter per second. And a joule, remember, is a Newton times a meter, which then comes out to be a Newton times a second. And actually for this problem, that might be a good way to leave the units. But remember, a Newton is a kilogram meter over a second squared. So the seconds would cancel off and you would be left with kilogram meters per second squared. And again, with those units, it might bother you because you've got mass showing up and you go, well, doesn't have any mass, but that's why Newton times a second might be a better way to write the units when you're talking about the momentum of a laser beam or the momentum of sunlight or the momentum of a radio wave. And I think C was it. Yeah, C was it. Let's just check then the solutions. 28, no, 20, what was this, 31. So let me scroll down here to 31. It says about 1,900. Good. They put 50 pico joules. Good. And they put 1.67 times 10 to the minus 19. And then they use the same units. Maybe not good. They should probably use those units. All right. Nice. All right. Hope that was somewhat helpful also. I hope you're seeing these are a lot shorter calculations than we've done in a long time. So I think these are relatively short problems. Most of the time we've been doing 1 page, sometimes 2 pages. Well, maybe a little bit, maybe about equal. Okay, so the next one here on my list is number 32. So let me try number 32. Just write that down, number 32. And the last one. Good. Like I said, these are a little shorter today. We might actually get done a little early today. Especially after the last couple of weeks. I'd be surprised. Okay, so 32 says, it says the intensity of sunlight at the Earth's distance from the sun is that 1,370 watts. Now, I mentioned that number back in 28. That's the upper atmosphere. So we'll keep reading, but we must be talking about the upper atmosphere, because by the time it goes through the atmosphere and gets down to ground level, an important number is about 1,000 watts per square meter. That's a number to work with when you're dealing with the surface of the sunlight, so like solar panels and stuff. But the upper part of the atmosphere, when it, just getting to the, and I guess that's how they phrase it, the intensity of the sunlight at the Earth's distance. Okay, so for getting the Earth just at the Earth distance is 1,370 watts per square meter. So A, assuming that the Earth absorbs all of the sunlight incidented upon it, find the total force that the sun exerts on the Earth due to this pressure. Okay, so this is very, very similar to one that I was saying before the break, where I spent some time in number 28 to talk about how there is a pressure and how there is momentum in light. And of course, we needed that because the problem we did in 28 was to build kind of a spaceship where the sunlight hit a large reflecting surface and bounced off. And as it bounced off, it pushed a satellite here or a spaceship forward. And that's what we're kind of talking about. We're not trying to push a spaceship forward in this case. We're just trying to say, hey, the Earth is getting bombarded with this solar light. And if you're telling me it's got a pressure, then that's pushing the Earth. You might say it's pushing the Earth out of orbit. And yeah, it is. But for these intensities, it's not a big deal. Now, there's some extreme cases in astronomy where the solar pressure is immensely important. And that solar pressure plays a big effect. Some great discussions that we can have here about the applied physics in astronomy. But I better stay focused on this problem for you guys here. So I'm going to say here that P, and P for pressure. Okay. We've seen a lot of P's here: momentum, power, and pressure. But pressure is force over area. So if you wanted to find the force on something, you would take the pressure and multiply it by the area. And that's, again, exactly what we did in number 28 here. In fact, we did this a lot in Physics 121, where the pressure then was the liquid pressure. So maybe we didn't do it too much. I guess that was the end in 14. We're going to do it a lot more in Physics 123 next semester, or half of you already did that in 123. And so the pressure, we're going to talk about an ideal gas, and we'll have like tires, pneumatic tires on your car, and say, okay, how much surface area do you need, or how much pressure do you need in order to hold up the weight of the car in order to get a force, or airbags for a collision, or airbags for stunt people jumping off buildings and whatnot. Okay, but for us, the pressure is coming from the sunlight. And so let me just come back here, because we derived that the pressure would be the intensity divided by the speed of light. So if you multiply by the area you're hitting, then that would give you the force. Now, we do need to be a little careful, because this problem is a little different than the 28 where we did the cell. We derived this for absorbing, and that's what this problem says. So we're going to use it. It says, assuming that the Earth absorbs all of this light. And so it's just like a hit and a catch. Whereas in number 28, we had to double this number, because the change in momentum was twice as big as just being absorbed. It was not just the momentum in it, but if light gets absorbed and then ricochets off, so like a baseball hitting a wall, it hits, comes to a stop, So that's loss of the momentum of the baseball. Then if it ricochets off at the same speed, then you got to give that momentum back, and the change in momentum is double. So, the momentum comes in with 10 and stops, that's just a change of 10. But if it comes in with 10 and bounces off, then it heads back with negative 10. That's a change of 20. From 10 to negative 10 is a change of 20. And so in 28, we needed to double this. But for this problem, we don't need to double. The absorbed momentum is exactly the same as the momentum that the light has. And so this is the equation of how much momentum does it have. All right, so if I put my 1,370 in here, and then again, divide it by 3 times 10 to the 8th, that'll be the pressure. And again, just want to emphasize what a small number that is. That's why, again, if you put your hand outside and the sunlight hit it, the last thing you would say is, oh, it's pushing my hand down. And likewise, pushing the earth out. I mean, granted, there is an enormous area, so maybe there's a decent number here, but I can't imagine it being much. And I think that's why they have part B, explain how this force compares to the Earth's gravitational attraction. So we'll talk about that in a moment. Okay, now we probably need to draw a little bit of a picture here to figure out what area we're talking about. So if I draw the sun with the light coming out, and then over here is planet Earth. I guess, first of all, you would say, well, the sunlight only hits half of it. So it wouldn't be the area of the whole sphere. And I totally agree with that. So if I have a good object to show, how about this lacrosse ball here? But if the sunlight is coming in, of course, the whole reason why things like up here in the northern hemisphere, the light just kind of hits at an angle, spreads it out over a bigger area. If you wanted to use the whole area of a half a hemisphere, you'd have to say the intensity changes over the slope. So another way of coming up with the same thing is to say, imagine cutting it in half, and you would have just a circle, and all that intensity is just hitting a flat circle. So that's the way I'm going to approach it, instead of saying it hits up in the northern or southern latitudes and spreads out over a bigger area, and so the intensity is lower, which is why you don't get very warm in the northern and southern peaks of our Earth, or the North and South Pole, or even, you don't have to go that far, but just to Alaska in the north, or south, I guess that'd be South America, Chile down there, how do you say that, Patagonia? And so anyways, what I'm trying to get at is this should be a pi r squared. Keep it accurate and to calculate it as simple as possible, so we don't have to use the area of a half a hemisphere. All right, so putting in our numbers, let's see what kind of force we're talking about. And again, I'll start with the pressure to give you an idea. 1,370 divided by the speed of light. So there's our pressure. And so you can imagine, putting your hand out there, it's just so small, especially when you multiply by a small area of a hand, it's not going to be much force. Now, it might add up to a significant amount of force once you multiply by the huge size of the Earth. So let me go times pi, and the radius of the Earth, 6.37 million meters is the radius. Okay, hope I'm remembering that right. I think I am. So 6.37 million meters and squared. And a bigger number than I gave it credit for. Still really small for such a big object, but it's 5.82 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Wow. Okay. I am glad we went through this number. I would have not guessed it that big. Now, I will guess that it is very, very small compared to what they're asking us to be. Well, how much is the gravitational force from the sun? Because the sun's pulling us in, so it looks like the solar pressure is pushing us out. And is it significant? I mean, would it matter if you went to calculate the orbit of it? Do you need to consider a combination effect of the force of gravity from the sun minus its own solar pressure? And I don't believe so. I believe this is just going to be, like 1 trillion times too small or some ridiculous amount. Let's see. And to answer this, we are going to go back to Physics 121. It was Newton's universal law of gravitation. The gravitational constant is 6.67 times 10 to the minus 11. Let's see, what do I know? The mass of the Earth, 5.98 times 10 to the 24. Mass of the sun, I want to say, is 1.99 times 10 to the 30th. We better look that one up. The distance, 1.5 times 10 to the 11th meters. I'm pretty confident on that one, but not enough. I shouldn't look it up here. So let me grab the book. I think the book has them all listed in the back flap pages. No? Maybe my first instinct was right. The front. There they are. Okay, solar system information. So the sun, 1.99 times 10 to the 30th. Good. Earth, 5.98 times 10 to the 24. I was pretty confident about that. There's the radius. Okay, good. I was pretty confident about that. But distance to the sun, 1.5. Okay, a little more accurate, 1.496. But it would be 50. The three significant figures. Okay, times 10 to the 11. So good. I was remembering right. And let's see how much gravitational force we get from the sun. So 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 is 1.99 times 10 to the 30th divided by 1.5 times 10 to the 11th squared. And, oh, wow. I said trillion. That's going to be hundreds of trillion. Okay. Even smaller than my guess. But it's 3.5 times 10 to the 22nd newtons. So if I take that number and divide it by the force from the solar pressure, we are, it's only 60 trillion. 60 trillion times greater. So again, you're talking about calculating the orbit of the sun and the effect of the solar pressure. Even something as large as the Earth, it's mostly just insignificant, and so we don't really consider it. But that's kind of maybe the point, or a secondary point of this problem, is to say, hey, there is a pressure. It could matter. The intensity is high enough, it could matter. In fact, I've seen some awesome experiments where they shine a laser beam vertically upward and then hit a small metal piece. I'll call it a BB. They can actually then stop the BB from falling and levitate it, or they can increase the intensity and shoot the BB. That's why there's some talk about using laser beams to project satellites. And there's a secondary effect too that I better not get into, but that could also be used. But I'll stay away from that. Let me just check the answer here. 32. 5.8 times 10 to the newtons away. 3.5 times 10 to the 22. and 60 trillion times bigger is in the opposite direction. It's repulsion. Okay, good. All right, so all that matches. All right, nice.